Hey everyone, this is Alex with Harvesting a Logistical Population. And I apologize for my handwriting in advance. Hopefully you can write stuff down for me. Okay, yeah, that's Jordan. Ignore him. Okay, so
I apologize.
I'm still
Wait,
recording.
I'm not
Okay,
you?
no, this is the take we're using, okay? I'm not doing another
Okay.
one. Okay, so harvesting a logistical population.
I apologize.
So we can represent this with the autonomous differential equation dx dt equals ax minus bx squared minus h. So this is really just a logistical equation with this extra minus h slapped on, and this is the harvesting rate per like whatever they give. So let's say you have like a population that reproduces at a rate of 6 worms per minute. So then whatever this number is going to be, it's going to be in terms of worms per minute. So this is going to be the rate of harvesting per unit of time. And so if we think back to section 2.1, we can rewrite this equation into dx over dt equals kx times the quantity of m minus x minus h, where this is just the logistic population again with the minus h slapped on. Oh yeah, keep in mind that all the variables in this equation are going to be positive. So if we're trying to find critical points for this equation to determine where its stability is, the first thing we want to do is multiply it out. So we'll get dx over dt equals negative kx squared plus kmx minus h. And so what we can actually do at this point is use the quadratic equation. We can plug these values into the quadratic equation, and then that'll give us our critical points. So, actually instead of solving for x on these, we're going to be solving for critical points labeled h and n, with h always being less than n. That's very important to keep in mind. So h comma n is going to be equal to negative km plus or minus the square root of k squared m squared minus 4 times negative k times negative h. And this is going to be all over negative 2k. So simplifying this down, we're going to get h and n are equal to m plus or minus the square root of m squared minus 4h over k all over 2. If you're wondering how we took out all the k's inside the radicand, it's because we took this k in the denominator. We brought it inside the square root, so it's 1 over k squared, and that just cancels out with this k squared term. And then it takes out one of the k's, and then you have 1k left over on the bottom. And so now that we have this general solution for critical points, we're going to go to example 4. So suppose you are a rabbit farmer. But your neighbor's rabid dog has infected your population. If you have a population of rabbits that is at the carrying capacity, then what is the maximum rate that rabies can spread through the population and in this scenario you can think of rabies just as a generic harvesting rate, so that's just going to be the H term. Without infecting every rabbit, after an infinite amount of time. And since we don't have enough information to actually give a definite answer to this, then we're just going to, or I'm just going to have you answer in terms of K and M for H. And then when you're done, also graph what the solution curves are going to look like for that differential equation. So pause or don't. Okay. So the first thing that we're going to want to look at is the radicand of the quadratic equation. So that's going to be m squared minus 4h over k. So if we look at this, we know that if you have this term being less than this term, so if 4h over k is less than m squared, which can also be written as 4h being less than km squared, then you will get 2 critical points. If 4h over k, or if 4h is equal to km squared, then you will get a singular critical point. Whoops. And if 4h is greater than km squared, then you will have 0 critical points. And this is because the radicand will become imaginary. So when we're trying to solve for the maximum rate or the maximum H value that we can have while still having a stable population, then we're really looking for the point where, or the highest possible H value that still yields at least 1 critical point. So if we look at this situation where 4h equals km squared, if you make 4h any larger than it is for that equation, then it's going to become greater with 0 critical points. So therefore, the point, or the H value that's going to be the biggest rate that rabies can spread through the population without all the rabbits getting infected after an infinite amount of time will be when 4h equals km squared. Boom. Good job if you got that. And then on to the graph. So when we're graphing this, or the solution curves, then since we have 1 critical point, we're going to label that as x equals h or n, because this value is just 0, so then if you do the whole plus minus thing, so you can see that. So since this value is 0, the plus minus doesn't change anything to the m over 2, and so h and m are going to be the same point. So then when you're graphing this, you will have a single line that's just straight. And if you think about the equation we had to start, then if you have an x value above, then that quadratic term, so that's going to be the negative kx squared term, is going to be greater than this, which means that the solution curves are going to go down to this x equals h and n line. And then also, if you have a term that's less, then the harvesting rate is going to be larger than these combined terms. So it will also be going down. So this is actually what's known as a semi-stable critical point, because on top of it you have all the solution curves funneling into it, so it acts as a sink. And then below you have it acting as a spout, since the solution curves are going out. So it's like partially stable and partially unstable. So that's our graph. Good job if you got both of those two. And so if we look back to this equation, the dx dt equals negative kx squared plus xmx, or kmx minus h, and we plug in our critical points, then there's a lot of math between these two steps that you need to know. But pretty much what you get is k times n minus x times x minus h. And this is where it's really important to make sure that n is larger than h, because if you put, like, let's say you have 3 and 5, if you put the 3 here and the 5 here, that's going to make the quadratic term positive, and that's going to that's not going to be a logistic equation anymore. So yeah, just make sure to keep that in mind. And so on to example number 5. Let me get a new piece of paper real quick. All right, example number 5. So in this example, we're pretty much going to use the equation that we just wrote, the k times the quantity of n minus x times the quantity of x minus h. We're going to use that in a real world scenario. So, suppose you get a cold. And you decide to take medication, in quotes, from Juiced Up Joe. Now, Joe is a very shady individual. He always wears a trench coat. You can probably catch him on in dark alleys in city blocks. So, unbeknownst to you, Joe's claim that his medication supercharges your cells. You don't have to write all this down if you don't want to, by the way. Was a lie. And what it actually does is allow him to harvest them at a rate of 10 per day. So, if your brain cells have a normal limiting population of 7, well, just assume k equals 1 for this problem. What are the new threshold and limiting populations for your brain cells after Joe starts harvesting them? I know that was a very lengthy problem, but I hope the premise was worth it. So go ahead and pause the video so you have a chance to solve it by yourself. And we'll get to solving it now. So if we start with the equation, the kx times m minus x minus h, and we plug our values in, we'll get, since k is 1, you just have x on the outside, limiting population of 7 minus x, and then minus that harvesting rate of 10. So what we're going to do, like in example 4, or I guess before example 4, is we're going to multiply it out. So we will get negative x squared plus 7x minus 10 equals dx dt. So then solving for critical points, we'll actually just set this to 0 this time, because what we can do is factor this. We don't have to just run it through the quadratic equation. So when we factor this, we'll get 5 minus x times x minus 2. And if we look, this is actually in the exact same form as we had here. The dx dt equals k times n minus x times x minus h. And so for factoring, oh whoops, you guys couldn't see that, sorry about that. So for factoring these problems, since it's kind of confusing sometimes when the x squared term is negative, what you can do is, as long as you have the two numbers that are the factors of c and add up to make b, you can just make sure that the larger one is the n, so that's going to be at the very start. And so that now that we have this equation, we can just look at it and say that 5 is the new limiting population. And this is because this is the larger critical note, or the larger critical point. So that's going to be that line at the top. Like if you imagine this is the graph, and this is n, this is h, you're going to have something looking like this. So n is going to be the limiting population, which in this case is 5, and that makes 2 the threshold population. So good job if you got that. So I think, well, the majority of us would have been able to survive taking this medication, from Juiced Up Joe. Unfortunately, one of our colleagues, Andrew Kim, didn't have the prerequisite amount of brain cells to survive. So unfortunately, he's not going to be able to teach the final section. So on to you, Andrew.